This is the fourth lesson in the first part of Unit 5 for our calculus class. And in this video, we're going to talk a little bit more about antiderivatives and how they can be used in the real world. So here's a question, not really calculus related, but one that's going to get us started here. If we travel at 50 miles per hour for 4 hours, how far do we drive? Well, most students recognize that if we multiply our velocity times the length of time that we travel at that velocity, then we're going to end up with our distance. So 50 miles per hour, I'm going to write my units this way, miles over hours, times 4 hours. Now, if you notice in these units, we've got technically an hour in a numerator, an hour in the denominator. So as we multiply, those two are going to cancel. And what we're left with is 200. And with no hour units, the only unit that's left is miles. So we've got 200 miles per, 50 miles per hour times 4 hours is a total of 200 miles traveled. Now, to transition this concept into calculus, let's talk a little bit about the graphic representation of this. And the function shown here with this bold blue line is essentially an equation, y equals 50. And you'll notice that we're remaining at this constant velocity. Our y-axis is described as velocity in miles per hour. And by the way, miles per hour, not sure why my ink isn't showing up here. Miles per hour is a rate, and rates, as you recall, are derivatives. That's kind of interesting. So we've got the graph of a derivative here, y equals 50. We're showing the graph of a derivative. Recall that velocity is equal to the derivative of position. And if this velocity is constant at 50 miles per hour and we have these endpoints, basically time starting at 0 and ending at 4, time 0, 4 hours, well, the graph ends up creating a rectangle for which we can calculate the area. And the area is equal to the distance that we travel. 50 miles per hour, so 50 is the well, it's technically the height here because 50 is along this axis. So we've got 50 times our width, 4. 50 times 4 gives us the 200. And the units, miles per hour times hours, end up reducing to miles. So that's interesting. The area under this straight line represents our total accumulated change or accumulated distance that's been traveled. So what if the scenario gets a little bit more challenging? What if you travel 30 miles an hour for 2 hours, 40 miles an hour for half of an hour, and then 20 miles an hour for 4 hours? What's the total distance that you travel there? Well, using algebra, 30 miles an hour times 2 hours plus 40 miles an hour, miles per hour, times a half of an hour plus 20 miles per hour times 4 hours. Well, that should tell us the total amount of distance that's traveled because, again, in each of these cases, we've got hours that cancel, and the sum of this result, and this result, well, each one of those are miles, so the sum total should also be a measurement in miles. So this looks like 60, 20, and 80, so we're talking about a total of 160 miles traveled. What if we graph these rates and calculate the area underneath those lines? Would the answers match? Well, I'm going to create an XY axis here. Just give myself plenty of room to work. And I'll label the axes, say 10, 20, 30, 40, 50, 60. So we're again dealing with our velocity, miles per hour. And along our x-axis, we'll talk about hours. And I think this scale would be appropriate. Every 4 grid lines is 1 hour. So we can travel 30 miles an hour for 2 hours. That would be a velocity shown by this straight line. Then we jump to 40 miles an hour for half of an hour, would be this straight line. And then we drop to 20 miles an hour for 4 hours. So here's 1, 2, 3, 4 hours. Now, we know in the real world it'd be virtually impossible to change speeds this quickly, but in this sort of scenario we're instantaneously jumping to this velocity, and then we're instantaneously dropping to this velocity. The question at hand, though, is does the area under this line still represent a total of 160? And hopefully you recognize that it does. This particular rectangle is 2 hours wide, so we've got 2 hours by 30 miles per hour tall. Well, that's 60. This area is half of an hour wide by 40 miles per hour tall, and then this guy over here is 4 hours wide by 20 miles per hour tall. And certainly when we're talking about the areas of these rectangles, the grand total also equals 160. Now, it is extremely important that our units agree here. And so again, we were talking about hours times miles per hour, which leaves us with miles as a result. Hours times miles per hour, when multiplied, leaves us with miles as a result. If our units disagree, well, then this method is less meaningful. Not that it doesn't mean anything at all, but it's less meaningful. It's less useful for us. So this trick that we're starting to establish here almost always requires a measurement along our y-axis to be a derivative. For example, if our y-axis was measured as just miles, maybe the hours component wasn't in here, maybe miles is the measurement, then we'd be talking about a position relative to time. And if we were to use this area method, we'd have, a measurement of miles multiplied by hours, and in this particular case, 2 miles times 30 hours produces a unit. Well, we still get the number 60, but it produces a unit called a mile-hour unit. And that certainly, in this case, does not mean distance traveled. A mile-hour is not nearly the same as a simple unit such as miles. So perhaps we'll discuss more about that at another time, but the takeaway that I want you to really consider at this point is that the y-axis measures a rate, and rates tend to measure or indicate derivatives. And that's going to play nicely into our calculus concept very soon. So let's suppose that you measure your car's velocity every 2 seconds. How can you use the same principles from above to establish the distance that you've traveled? Now, this may seem kind of unusual at first, but really it's not too hard, especially if our units were more common to what we see in a vehicle. So I'm just arbitrarily going to change these. Well, I shouldn't say arbitrarily. I'm very specifically going to change these. So time, I'm going to just say is hours, and I'm going to say velocity is miles per hour. And the reason why I'm changing that is, well, first off, I want my time units to agree. I want hours in the top row and hours in the bottom row as well. But miles per hour, this is a measurement that we can easily read off of our speedometer. You can simply look down at your speedometer and report the velocity that you're traveling at any given time. And so if you had a friend in the car, you could essentially look at your speedometer and call out the velocity at given time increments. So at time 0, your friend could ask for the velocity, and you can report 20 miles an hour. At time 2, you can report that you're traveling 30 miles an hour. At time 4, you're traveling at 38 miles per hour, and so on. And so I realized that, we're not going to be driving in the car for 10 hours, and we're not going to be driving this slow in a car for that amount of time. So I'm actually going to switch back to the original measurements here to complete this analysis. But I did want to just talk about that quickly to show the connection to the real world and how it can be made. So now we're going to pretend that our car is producing a readout of telling us our velocity in feet per second, and we call out that velocity every 2 seconds. Now let's go ahead and graph those velocities over time and see what we get. So I had to adjust the graph just a little bit here. I think along the x-axis, this would be every 2 grid lines representing 1 second. And on the y-axis, hopefully you have enough room in your printout, every 2 grid lines I've marked at 10 miles per hour. In doing so, we'll be able to plot each of these coordinates. So I'm going to put a dot at 0, 20, because at time 0 we were traveling 20 feet per second. At 2 we were traveling 30, and so on. And so here are the data points, and you can imagine that in between each of these data points, the velocity of the car was increasing at more of a smooth interval. It wasn't nearly as choppy as what we saw in the prior examples. And so now the question becomes, well, how do I find the area underneath a curve? The area underneath the straight line up here wasn't too challenging, but the area under a curve can be a bit more difficult. I don't have a rule that helps me find the area under a curve like this. Now, if it was a perfect semicircle or something like that, that may be different. We might be able to find a way through that. But under a curve that follows an unknown path, I mean, we don't even have a function that establishes this curve. How are we supposed to find the area under it? Well, one of the most common methods is to simply draw rectangles that fit underneath the curve. And what I'm going to note here is that we have 2-second intervals between 0 and 2, 2 and 4, 4 and 6, and so on. We could essentially create rectangles that fit underneath this curve. And so I'm going to cheat with my electronic ink, and I'm going to start on the left-hand side of this interval between 0 and 2. This data point is on the left-hand side, so if I draw a rectangle that fits underneath the curve, because it starts on this left-hand side here and the curve is increasing away from it, that area can easily be calculated. And I know the height and the width of this curve because, well, the interval itself was established to be 2 seconds, and the height, well, this was a data point given to us at time 0. At time 0, the height was 20 feet per second. I can draw another rectangle for the next interval, and it's going to start at this data point. Here again, the height of the rectangle is given to us because that was a measurement at 2 seconds. We were traveling 30 feet per second, and so on. So if I continue to build these rectangles on the left-hand side, or beginning on the left-hand side of the interval, I can create a whole series of rectangles, and that should give me the area underneath the curve. Now we're going to stop right here. We're stopping right here because we don't actually have information beyond the 10-second mark. Our graph should stop right there for the time being because, again, our data ended here. I ended up with 5 rectangles underneath, and each one is 2 seconds in width, or 2 units in width, and the height is described by the data values at 0, 2, 4, 6, and 8. So each of these first 5 data points represented the heights of these rectangles. Now clearly, if my objective was to measure the area underneath the curve, this is going to be an underestimate because there are sections between each of these rectangles that are left over that we haven't accounted for inside of that curve. So 20 times 2 plus 30 times 2 and so on. When we sum those products together, will give us a distance traveled. The units tend to agree, feet per second times seconds reduced to feet. And so the sum of these come up to 360 feet. And in this particular instance, that would be an underestimate because all of our rectangles were underneath the graph. Now I could use a very similar process, but draw each of the rectangles from the right-hand side of each of these intervals. And let's say I build a right-handed rectangle. And that does sound a bit strange, a right-handed rectangle. Well, I'm calling it a right-handed rectangle because I'm building the rectangle based on the right-hand side of each interval. So between the interval of 0 and 2, I'm looking at the height established by the y value at time 2. between 2 and 4, I'm looking at the height based on the value at 4, then the value based on 6, then the height at 8, and then finally the height of the rectangle at 10. Pretty quickly you'll see that this is now an overestimate because each of these rectangles is slightly taller than the actual curve. It's taller than the curve by a little bit. And if we do the math here, using the right-hand sums, we sometimes call this, all of the data points from 2 through 10 were used to create the heights of these rectangles. So the heights are now from 30 up to 50. Well, as we calculate the area of each of these rectangles and sum them together, we get 420 feet. And this, again, is an overestimate because every one of these rectangles is taller than the curve itself. So the area inside of these green boxes is greater than the area underneath that curve. So what would you do to find a better estimate? Well, hopefully you're thinking we can just find the average of those two. If we find the average of 390 and 420, well, that's going to come out to be, sorry, I reported that wrong here, 360. The average of 360 and 420 is 390 feet. And that might be a better approximation, too. I don't think it'll be perfect, though, but it'll be a better approximation than the underestimate and the overestimate exclusively. So if we didn't have a tool measuring the distance that we traveled for these 10 seconds, we can actually pretty easily compute it with just 5 or 6 data points. In this case, we used 6 of them. In our first calculation, we underestimated the total. In our second calculation, we overestimated our total distance traveled. But then if we averaged the 2 of them, we found a pretty good approximation, I would argue. But we could do better if we had some additional information. Perhaps you already looked ahead and saw, well, couldn't we just increase our accuracy by introducing more time intervals? What would happen to our estimations if we calculated the area every second rather than every 2 seconds? So in this chart, you can see the same information at 0, 2, 4, 6, 8, and 10, but in between those measurements, we've got other pieces of data to work with. Now, effectively, what that does is it creates many more rectangles that are a bit narrower, but they'll more closely approximate the actual results. So in this sketch that's here and provided, you can see the underestimates in this darker blue and the overestimates in the lighter blue superimposed on top of one another. If we're dealing with additional data points at time 1, 3, 5, 7, and 9, we can actually draw rectangles in between and get even better estimates still. So this rectangle starting at 1 will fit right about here. This rectangle starting at 3 fits in place here. Take a look at what's happening at this point now. Our underestimates, and these are all underestimates still because these are what we would consider left-hand sums of an increasing function. The function itself is increasing, the velocity is increasing at all times, so each of these rectangles that we build are still underneath the curve, so this is what we would consider an underestimate. But by introducing a second rectangle, you'll notice where the old underestimate was, it was right here. Well, now we've got a second rectangle that's actually taking up some of that space that was not captured by the first underestimate. And in this next interval, here's our old underestimate, our first left-handed sum, but now this second right-handed sum sneaks in there as well. And so each of these additional rectangles is giving us a slightly better approximation for the area under the curve. And in a similar argument, the overestimate isn't quite so bad. If we were to come through and draw all of the overestimates again, well, they're only slightly larger than the curve itself. So if I were to use a right-hand rectangle here, and then a right-hand rectangle here, that would effectively eliminate this overestimation. This component right here would go away. And then we can come through with a right-hand rectangle here, and a right-hand rectangle based on that interval, and then this overestimate would go away, and so on. Now that is going to change our calculations just a little bit. Now every rectangle, instead of being 2 units wide, is only 1 unit wide. But the height values, well, we get to be a bit more specific, and we want 1 unit in width times 20, 1 unit in width times 26, and so on, all the way down to this second to last data point, 1 unit in width times 49. And this process is what we would call a left-hand sum, because we're going to add up all rectangles that were established with left-hand data points. And this sum comes out to be 378 feet. And again, horizontal unit of measure was seconds. The vertical unit of measure was feet per second. Those units will effectively cancel and produce a unit of feet. For our right-hand sums, we're effectively using the numbers 26 up through 50 for the heights of each rectangle. And again, we're going to call this a right-hand sum because we're adding together all of the areas from rectangles created with right-hand data points. And this right-hand sum comes out to be 408 feet. Clearly, these estimates are better. They're not perfect, but what was 360 feet as our initial left-hand sum, and with 420 as our initial right-hand sum, we can clearly see that our estimates are getting at least a little bit better, or at least in a tighter range of possible solutions. And so, of course, it stands to reason that if we can increase the number of intervals even more, then the accuracy will, of course, improve. This chart shows what the graph might look like if we took our velocity measurements every half of a second or every quarter of a second. And if we could record an infinite number of times, so an infinite number of intervals. Again, I apologize for the ink that keeps disappearing, but if we had an infinite number of intervals, well then we would have virtually no rectangles at all. We'd have essentially an infinite number of vertical lines whose areas represent the area underneath the curve. And clearly, from a geometric perspective, that can't be done. We cannot calculate the area of a line. A line has no width to it. It only has a single dimension, so we can't calculate the area. But what if we could? What if the number of intervals increase towards infinity? What if I use the letter n to represent the number of intervals? And originally we had 5 intervals, then we went to 10, and then we went to 20 and 40. What if we approach an infinite number of intervals? How on earth could we use calculus to make that happen? Well, limits are the answer. We've seen those before. Essentially what happens is, since we're adding together all of these areas, we have to introduce or reintroduce summation notation, and you've probably seen this before. This capital sigma indicates that based on the following function, we're going to add together a bunch of results. So I'm going to let delta x represent the horizontal distance, or the horizontal change in x, based on the number of intervals that we've produced. And if I had that horizontal distance, or the width of the rectangle, multiplied by the height of the rectangle, which is calculated by establishing the function's result based on the x value. And if I added all of those together from one interval up to an infinite number of intervals, I should use the letter n here, from 1 to n, and this wild-looking expression does give us the area under a curve, area based on x underneath a curve. Now, a minute ago I called this capital letter sigma, and that's important because the word sigma in current language, not Greek language, but in current language actually starts with the letter S. And we know how fancy people used to write back in the olden days, so they like to write that letter S as kind of a scripted, curly S. And we'll provide some boundaries here just because we can. In this particular example, we're timing the car from 0 up to 10. And certainly if I had some data points, I could establish the function that creates that curve, and we'll call that function f of x with respect to the change in x, delta x, change in x, multiplied by the height of our function. I'm just going to reorder that a little bit so that it looks a bit more familiar. So here's the height of the function at any given point. Here's the width of those rectangles. Is this expression starting to look a little bit familiar? Hopefully it does, because this expression too can be used to help us calculate the area underneath the curve. So with that being said, I'm going to stop the video here, and we're going to pick up with this notion of areas underneath the curve using calculus and integrals or integration in order to find the area underneath the curve, because it's this integration technique that essentially allows us to create an infinite number of rectangles, infinitely narrow, but an infinite number of them underneath the curve, and those rectangles, the sum of all of those rectangles, will ultimately give us the exact and precise area underneath the curve if we know the equation that established the curve. So I would encourage you to do some more research on your own if you wanted to learn a little bit more about this before we talk about it together in class next week. Otherwise, if you have questions with the work that's been completed this week, please let me know. I'd be more than happy to help. Thanks for watching.